So let's throw in a third definition of acids, just for fun. We talked about the Arrhenius acids, which are substances that form hydrogen ions in aqueous solution. We talked about Bronsted-Lowry acids, which are acids that donate hydrogen ions or donate protons. The Lewis definition is going to focus on an electron pair rather than a proton. So an acid is an electron pair acceptor. It's a proton donor. A base is an electron pair donor. So here we have ammonia. Nitrogen has a lone pair on it. It can donate this lone pair to hydrogen. So this is acting as the base, the electron pair donor. This is acting as the acid because it's accepting the electron pair. They would still be defined the same acid or base with the other definitions. So they don't contradict each other. And like the quote at the beginning of the chapter said, it's not about which one is better, but which one's more convenient in different situations. So this expands the definition of substances that can be considered acids, because now an acid does not have to have hydrogen on it. The good news is we're not going to do any naming of things like that and change names or anything. We're not going to do that. But a Lewis acid doesn't have to have hydrogen. BF3 acts as a Lewis acid. A Lewis acid will accept electrons, an electron pair. Here's our familiar ammonia, a Lewis base. It has an electron pair. It can donate. Boron is one of those guys that has an incomplete octet. So, if you draw the Lewis structure of that, you could put a double bond in there and make it have an octet, but then the formal charges are all off. So that's what it is. So here, boron only has 6 electrons instead of 8. And so when this guy gets near that guy, and this one's like, well, I'm willing to share a pair of electrons with you, boron's like, oh, that would just make me super happy. And so they get together. And when a Lewis acid and a Lewis base combine, they're called an adduct. So what's a little different here is instead of, an acid handing off a proton to the base and then they go their separate ways. Here, the electrons are being donated, but they stay together. So Lewis acids are going to have empty orbitals, or they're able to rearrange their electrons to create empty orbitals that can accept the electron pair. Yeah?
Is there a rule to how the product is written out because we switched when they are added together?
The F and the B?
Yeah.
Yeah. So they wrote the B second because the B is where the electron pair is. And so that's why they wrote the F3 first. It's a great observation. Any other questions? Definitely not going to trick you with that.
This is Kay.
Yes.
The Lewis dot structure for NH3,
Mm-hmm.
does that look the same as the BF3?
That's a good question. So that's the BF3. And you're asking about the NH3? Yeah. So NH3 is going to have a lone pair on the nitrogen. This has a full octet, 2, 4, 6, 8. This does not have a full octet. So this electron pair can get shared with the boron. It's not an equal sharing. It's like, oh, I feel so sorry for you. I have 2 electrons here. I'll share both of them with you so we can make a bond. I'm so generous. It's called a coordinate covalent bond. Does that help at all?
I remember that name.
Well, that's good. This one has a lone pair of electrons, so that can be the base. This one has an empty orbital. It's missing. This is a fairly stable compound. Boron is so small that, it can be talked into running around with only 6 electrons instead of 8. But if it has an opportunity to get 8, it's going to take it. So here we have aluminum trichloride. The aluminum has incomplete octets, and so that's where this electron pair can donate to the aluminum, and those can form an adduct. They can get together.
So we'd write that Cl3Al in.
Yeah. Yeah, I believe you'd write that. Cl3AlNH3. There's several things in Chem 1B that the reason we teach them to you is because you're going to need to know them in OChem, right? And so you're going to need to know what Lewis acids and bases are in organic chemistry, because that's most of what they deal with, because a lot of their solutions are not aqueous, right? There's no water involved. This is an organic compound. This is an ether, diethyl ether. The oxygen here has 2 lone pairs. Here's boron trichloride. Boron has an incomplete octet. Oxygen can donate electron pair to the boron, and now boron's extra happy. This would not be considered an acid under the definitions from Arrhenius or Bronsted-Lowry. It's not going to form hydrogen ions in solution, and it's not going to donate protons either. And this is just a taste of fun to come in OChem. Electrons moving around. So here we have carbon dioxide. Carbon dioxide is a Lewis acid. And here we have water. Water is a Lewis base. Well, carbon here has a complete octet. So why would it do this? Well, it can move its electrons around. So it can move a pair of electrons onto the oxygen. When it does that, the oxygen still has an octet, and now the carbon only has 6. So then it makes room for this pair of electrons to come over. And then this hydrogen can come off. It leaves its electrons behind over here, and it can bond to this pair over there. And that's carbonic acid. I don't expect you to remember that. It's kind of cool, though. And can you imagine all the thinking and experimenting that went into, not just thinking this up, but actually demonstrating that that's actually what happens. That's hard.
It's so much fucking around and finding out.
Yes. Some cations can act as Lewis acids. Typically, small, highly charged metal ions. Have we heard those before? Yeah. Which ones did I tell you to remember? Iron and aluminum, right? We got Al and Iron Man. That's new for this semester, by the way. I don't know where it came from, but I like it. So here's aluminum acting as a Lewis acid. Here's water acting as a Lewis base. 6 of these are going to come around and donate electrons to aluminum, and now aluminum's just like in heaven. There are other metal ions that can do this. The aluminum has empty orbitals because it lost some of its electrons.